Good morning, good afternoon, everyone. So this meeting is recorded. So we plan to post this on YouTube. If anything occurs during your presentation or the question that you think you would prefer that we edit out, please let us know after the meeting, and then we'll do that before we post it. Today we have a presentation from Atina and Manu from Friedman Zenke Group in Switzerland. And so they kindly agreed to present this publication that I have on the agenda, Understanding Neural Circuit Principle for Representational Learning. This was Farzaneh pointed out, Najafi, that this paper will be of interest, so I reached out and they kindly agreed to present. So we're looking forward to your talk.
Thank you. So I will quickly share it again. Okay. Thanks for having us today. Yeah, we are going to present this project today, where the question is really how we learn. So our day-to-day experience is similar to watching this video. Objects and animals around us are moving around, and this information goes through our brain as a stream of information. So at each time point, this information goes to our brain through our eyes, and we can recognize that, for example, there is a bunny at this particular moment in time, at this particular location, moving with some velocity. Its body is oriented in such a way, and it is moving to left with some angular speed. And all this information we learn through our experience, and there is no one standing beside us telling us all these labels. So it is learned in a self-supervised manner from our own experience. So to make it more robust, these variables that underlie our sensory experience form a space where, for example, each animal or each object can be represented as a manifold in this space, and a trajectory within each of these manifolds can represent the movement. But what we experience in the sensory input, it is very entangled, and this information is not really easily accessible. So what happens is that this information, as it goes through our brain through time, the brain has its own way to presumably untangle this information so that all this information is accessible to downstream network, so that we have an understanding of what is moving and how it is moving. And then if I see another animal, this trajectory can be represented on the corresponding manifold and easily accessible again. And the big question is, how does the brain learn the latent variables that underlie this sensory experience? We are going to address this question by modeling it and using artificial neural networks as our model system. In this framework, we basically try to come up with the theory for learning such representations, and we rely on one major computation that we know happens in the brain, which is prediction. So there is numerous evidence for predictive processing in the cortical networks. For instance, our neighboring lab, your killer lab, have these virtual reality where they have these local and global sensory motor mismatches, and show the response in both neuronal and population level to mismatches to the what animal is expecting and what it's deviant from the expectation. There is also rising evidence for predictive learning in the brain, and how prediction can shape learning of spatiotemporal sequences, and also shape the representational geometry of, for example, human brain. So prediction is principal computation that we can benefit from in modeling how the brain can learn latent variables, presumably. Predictive processing per se is usually framed under classical predictive coding framework, where the assumption is that higher circuits in the brain make predictions of lower circuits down to the input space. Then this prediction is compared and the error is sent forward in the hierarchy. While this has shown promises in explaining experimental evidences, there are a couple of flaws when you try to implement this framework in computational models. For example, this backpropagation of the prediction within the hierarchy implies that at the lowest circuit, you have to compare your raw sensory input with what is predicted, which means that you will have a back projection to retina, compute an error at the level of retina, and send this error to the brain, which to our understanding, there is not much evidence for. Also, from a computational perspective, this type of error computation and optimization is prone to basically, it is sensitive to noise. So it is prone to forget about information that is relevant for perception. Also, another flaw that usually in computational models that implement predictive coding we see is die-out activity. Since you always try to send the residuals up in the hierarchy, the higher you go in the network, you have less and less activity. Presumably, it also dies out, and there are no representations that are informative of the underlying latents at higher circuits, which is clearly not how our brain works. For example, infratemporal cortex, which is thought to be one of the higher areas in the visual processing hierarchy, can have information about the objects, whereas in such cases, it is quite like vague if this information is in the network. It is usually not studied properly. So we decided to look into a more machine learning grounded approach, which is joint embedding predictive architecture, or JEPA for short, which has also been discussed recently to match to cortical computation for predictive processing. How JEPAs work is basically they use two processing streams. One of them we call prediction stream, the other one the target stream. There are basically encoders that encode the information, the input, into some embedding space, and then the prediction processing stream has an additional network that receives these embeddings and tries to predict the the predicted embedding from the other stream, basically. And the optimization is done by optimizing for this distance measure, which is basically the prediction error. So you want. And one of the important factors here is that the learning signal is only backpropagated through the prediction stream and not the target stream. So whenever you see in the presentation dashed line, it means that the error signal, the learning signal is not backpropagated through that processing stream. And then you can have JEPAs that have different encoders in the two streams or have the same. These enable us to have self-supervised learning without requiring labels. And also, you're not predicting the actual input space, but in some embedding space, so it is reconstruction-free, and as a consequence, it avoids noisy features. But as I told you, joint embedding predictive architectures are machine learning methods, so they use mostly transformer backbones. And also, the learning task that's they are usually employing is based on random spatial and temporal masking, which, for example, random temporal masking can defy temporal locality. So it is still a gap to be able to come up. Yes, there is a question.
Yeah, just a clarification. In
Mm-hmm.
your mind, the X is, let's say, for instance, X could be the visual information and Y the motor response.
There are different interpretations in JPAS. How it is treated is usually X and Y are different augmentations of the same image, but they can be also different modalities. For example, X can be audio and Y can be X can be raw audio, Y can be the spectrum. You can think of it as X being input at time T, Y being input at time T plus delta. There are these different interpretations that you can have through JPass. So you have quite an open hand in how you want to treat it. But the two inputs should be relevant. That's quite a key in designing this. And the action is usually used to condition the predictor. It is not shown here, but how usually in machine learning they embed action is they somehow integrate it into the predictor so that the predictor has the information of what is the action or the transformation between the two inputs. So it is not directly given to the encoder usually. Yeah, so since there are these problems that basically make some gap between how we can match it to neural architecture, we decided to, instead of using transformers, we just stick to feed-forward network for the encoder, and then for the predictor, we use a combination of a recurrent integrator and a feed-forward predictor. So in general, what we propose looks something like this. So at the beginning, we have a feed-forward instantaneous encoder that receives instantaneous information from the input, embeds it into the embedding space. Then a recurrent network, which we call integrator, gets these embeddings through time, integrated through time, and forms the representations of the model. These representations are then fed to the feed-forward predictor to make a prediction of the future embedding instead of the future input directly. And then the network is optimized through the loss, which is basically optimizing for the prediction error. So this basically architecture plus the learning rule is what we call recurrent predictive learning, or RPL. Which defines specific computational components that hopefully we can find some collaterals with what the brain can have in different granularities. So first of all, we have to see if it works. To test this, we generate a data set where we have control over all variables. We basically choose one of these 8 animals, put it into the space. These animals can move with constant velocity, and the motion in the third dimension is basically represented by zooming in and zooming out the image. They can rotate with constant velocity, and also when it hits the ball, it bumps. So in sensory space, this is how the video looks like. We also add some noise on top to make it a bit more complicated for the network. Videos of such are given to our architecture. We optimize for the prediction error. After the network has learned and converged, we basically freeze all the parameters, and we train a linear readout on the integrator, or what we call the representations, to extract the information of these variables and see if the model has learned these information from seeing these videos. And what we observe is that actually our model RPL in red learns to extract different latent variables, including what is the object, where it is, what is its velocity, what is its orientation, and what is overall rotation speed throughout the trajectory. And the performance is reliably close to an end-to-end supervised training baseline where you give the labels at each time point to the network. The dashed line represents the case where you have the same architecture, but you initialize the network randomly and then train just the linear readout. In the beginning, I told you that to have this nice decodability in downstream neurons, one would presume that there is this structured representation space. To check if the representation space of our model is structured, we plotted the projections up to the coding directions of velocity and orientations, and we can see emerging squared sheets and circles for velocity and orientation respectively, which mimics the ground truth latent structure quite nicely. Then we wondered whether, yes?
I have a question. Oh, no, Sarah is first.
Well, maybe I have a similar question. I have a very naive question about your assumptions in terms of the data that you're using. So is the velocity that is constant for the bunny a different velocity than the one for the whatever the corgi? And
Yeah.
how much does it matter that these parameters are constant? Because I mean, from the video you showed off, right? You imagine that this is constantly varying, and the same for orientation, for instance. I just wonder whether this is kind of a given that you're going to have these separations based on the assumptions that you made.
Yeah, so to be more clear, the velocity and also the rotation velocity are sampled randomly for each of the videos. So one video can be a bunny with one particular velocity, and another video can be another animal with another different velocity. The only thing is that the velocity is constant throughout a single video. That's what is constant.
But in reality, right, that's the one thing that would probably vary dramatically from
Yes,
one
of
frame
course.
to the next. Yeah, so I'm wondering how much does it matter to you that this is constant at this stage?
So this basically gives us the opportunity to have it as a linear variable. And it basically is easier to decode it linearly. If you can have like also acceleration or more complicated types of movement, but then the downstream network might require to be more complicated and nonlinear instead of linear. Then it is not a big deal, but if we have basically the ability to decode information linearly, this means that this can give us a better insight in how the representation space is formed and how accessible the information is. Because if you have a nonlinear network on top, you can have more computation in the readout rather than what the actual model is doing.
Okay, got it. Thanks.
I also want to pitch in here just to point out that the velocity does change within a given video when it hits the walls. So then that's a reflection. And even though the angular velocity is constant, the orientation kind of changes from frame to frame in a continuous way.
Yeah, of course, because the rotation.
So we do have both invariant and dynamical variables.
Okay, I have it's not slightly related, but my experience with these machine learning models that try to learn latents is that very often they impose some constraint in the optimizer to force the latent to be independent of one another, or there are some constraint to separate the latent. Like I think sometimes they use multiple informations or things like that. And so in your training, I didn't see any constraints. So how does it learn separate latents?
So yeah, you're correct. This is the loss that we have. And the point is that in JPOS, usually this basically SG, the stop gradient, basically helps to basically implement an implicit variance regularizer. It is also like nicely shown in a recent paper from Fabian in such temporal predictive JEPAs. This can arise naturally. So this is implicitly handled by the model. And also just an additional detail for those in the room that are more machine learning friendly, we also use weight decay. So there is this type of regularization, and that's the only thing that we have in addition to this actual loss.
Okay, and then you interpreted the latent to say which one is which one is the speed, or which one. This was like a manual step.
Yes, yes, but it's basically a linear decoder to see if this information is there. So there is no complicated computation in the readout. If this information has been learned in the model, it should be extractable by the readout. And that's it.
Okay, great.
Cool. Okay. So by now I've showed you that it learns the latent variables, but another essential factor for any predictive agent is to simulate the future trajectory, which can basically enable you to plan ahead or fill in the information that might be missing in the future. For example, something is covering your field of view. So to test that, we basically first gave a couple of frames of one video and decoded the position. This is the 2D, and this is the basically third dimension. The black is the full trajectory of the true video, and the red shaded part is basically the decoded information from the input. And then we shut down the input and feed the output of the network to itself in an autoregressive manner, and again try to reconstruct the trajectory. And as you can see now, the continued red line can resemble quite nicely the true trajectory. Also, we made sure that the animal that was in the video stays the same throughout this simulation process. And also we checked if we can reconstruct the other latent factors like the velocities and orientation. Then we did this for multiple unseen videos, computed a mean-squared error for decoding each of the latent variables, and this is what I am showing here. The gray part is where it still sees the inputs. The rest is where it gets its own output as input. And as you can see in the beginning, the error is very low. And as the simulation process goes on, then it starts to deviate, which is to be expected. So to sum up what I have showed you so far, I introduced RPL with this very specific circuit architecture and different computational components that is able to learn the latent structure and simulates future trajectory. If there are no questions so far, Manu will explain why this particular circuit architecture matters.
I'm assuming going to speak about neurons in real brains in the next section. Okay, great.
Yes.
A little bit, yes. Unfortunately, I can't do the multi-presenter slideshow for some reason. So what I'm going to do is just share my screen instead. Do you guys see my slides by any chance? No.
We can see. Oh.
Yes.
Interim summary one?
Yes, perfect. Well, I have to find it myself.
Oh, now you see desktop too. Oh.
Okay, good. Hopefully now it works.
Yes.
Okay, perfect. So right. We just saw that RPL, which is this very specific predictive learning architecture, can learn a latent structure of these variables and possibly simulate future trajectories. However, I mean, you guys might have noticed that this is a very specific circuit structure, the way things are set up and the prediction target that's actually optimized in the prediction error. There are multiple different possibilities. For example, even if uh, we say we don't want to predict in the input space in the raw pixel space X, we don't want to do reconstruction. Even then, there are other different parts in the network which can which can function as prediction targets. For example, this is an important alternative called which we call invariance learning, where the prediction target is the output of this predictor right at the top of the hierarchy, network hierarchy. So the prediction target is at the same level as where the prediction is generated, right? So we call this invariance learning because this circuit structure is driven to minimize changes at the same level. So it's going to learn more invariant features. So for technical reasons, this kind of objective does require explicit additional regularization objectives to learn non-trivial features. In machine learning terms, these are called joint embedding architectures, basically without the predictive part of JEPAs. So specifically, like the JEA method that we use is called LPL from prior work from the lab. So like I said, this architecture is geared towards learning features that are more invariant across time. And so what will happen when we when we learn with with this new learning structure on the same moving animals data sets is instead of getting these nicely structured latent variable representations, we end up with basically not informative, non-informative representations, at least for the latent variables that actually change. Whereas you still see that there's encoding of object identity or which animal is actually present. And quantitatively, what this means is like decoding accuracy for object identity or animal identity is still high with both IL and RPL, but decoding accuracy for dynamic variables such as position, velocity, orientation, and rotation speed is highly degraded when we optimize for invariance learning. These observations also hold true in more naturalistic data set. For example, these videos of mice moving around in an open arena, where we can label those videos again manually, well, using some processing pipelines to label it with velocities, body orientation, and position, train RPL and IL on these videos, and then again ask whether we can decode these underlying latent variables. And again, IL seems to struggle much more. This also holds more cleanly in a natural speech data set. To be specific, this comes from a data set called Libri Speech of spoken text, where there are labels that exist at the level of who is speaking, speaker identity, as well as more fine-grained dynamic labels of what phoneme is being spoken at each instant. So again, like we expose RPL and IL to this data set, to this data, it has no, again, like it has no information about labels. We do that downstream with the linear readout. And again, RPL is able to learn both speaker and phonemes, whereas IL is only able to learn speaker identity because, again, speaker identity is kind of an invariant quantity that stays constant over a given speech sequence, whereas phonemes vary much more quickly. There's something wrong with with the slides here, but hopefully you can still see the content. So there's another variant where the prediction target, instead of the output of the instantaneous encoder, we can ask the network to optimize for predicting the output of the integrator instead. So effectively, what this does is now we instead of a feed forward encoder, we now have a recurrent encoder that's more contextual. So we call this context predictive learning, or CL for short. And the learning objective is again very similar to RPL, except now the prediction target is C T plus delta instead of Z T plus delta. So hopefully you can see the small, like seemingly small difference between these two architectures. But there is a failure mode that arises from making both the prediction target and the prediction source recurrent, which is that like the integrator is an RNN, which can, in principle, also generate its own predictable signals, such as a sinusoid, for example. This would be perfectly allowed by this learning architecture, and it would minimize this, given that if, for example, that sinusoid has the right frequency, right? And we assume that such self-generated predictive features are more likely when the underlying prediction task, which actually respects the dynamics of the inputs, become more difficult to learn. And by this, I mean, for example, if we add more noise, the prediction task becomes harder. So CL, with its recurrent encoder, is more incentivized to generate its own features. And that's kind of what we see in this indirect study, where as we increase noise in the pixels of the animal videos, RPL remains fairly robust in terms of encoding all of the different latent variables, whereas this context predictive learning objective degrades significantly with higher noise. We see a similar observation where CL degrades if we occlude more frames in the video, so then prediction does become harder. It needs to rely more on the recurrence. Again, like RPL is robust, whereas CL degrades across more and more difficult prediction tasks. So just to summarize, we have RPL with this very specific predictive learning circuit. Invariance, so alternative architectures such as invariance learning and context predictive learning, where you have either prediction targets at the same level as the prediction source, or you have recurrent encoders. These have very specific failure modes, and that is why I think the takeaway here is that an instantaneous prediction target is actually essential for learning predictive representations of the latent variables. So just to summarize what we've seen so far, we have RPL, which can learn latent structure from synthetic and natural streams, and it needs to have this very specific structure. It can simulate feature trajectory, but is this consistent with experimental observations, right? Like that's what I think at the end we all care about. So we have some studies that find some predictive representations in the cortex, and our model is able to reproduce these effects qualitatively. For example, there's one study from Floris Lange's lab recently where they found successor-like representations in human V1 in fMRI recordings. And the way this works was humans were habituated to sequences AB of the form ABCD. And then after habituation, they would present isolated stimuli among these four, and then look at whether successor or predecessor representations are activated upon presentation of a given stimulus. So what they saw was quite clear. Given a stimulus, only successor stimuli do get also activated in a predictive way, whereas predecessor stimuli are either inactive or slightly suppressed. We modeled this type of paradigm where we habituated a small toy RPL model with sequences of this sort. And again, we see very similar effects where only successor stimuli, successor representations are activated when a given stimulus is presented, but not predecessor representations. A little bit more sophisticated experiment with macaques where recordings were, yep, sorry, yes.
Can you explain a little bit how the comparison between the neuronal data and the models was done here?
So here it's in a sense that we record neurons in our model in the same way that they recorded in the fMRI in some sense, right? Like we have.
So it is a very toy setting, basically. Instead of having a visual stimulus, we just have the ABCD sequence as a one-hot encoding. And then we have 4 neurons in each of the computation components that we mentioned before. And then we look at the integrator, or where we call the representations. If you can basically extract these successor information or predecessor information. So we have additional readouts to basically see the selectivity of the neurons to each of the elements of the sequence, and then basically see if we can read out the next, for example, if we are showing B, can the neurons that are selective to C also show activation or not? Basically, this is the paradigm.
I'm not sure I fully. So maybe when I've seen previous studies doing similar things, they do a similarity analysis. Like they have the models that is trained on the same task, and they have the recording, and they try to see how similar are the representations from the neural data to. Is that what you did here? Or?
So here we don't have the actual recordings. Also the it is more like basically what they showed in the experiments. So they basically, this is literally what they show. They show what is the bold activity from the fMRI data, and we don't have any of the fMRI recordings. We don't have access to that to actually like look in more details into representation similarity or these things. So we just look at how the overall bold activity as they report it, and then we try to have basically single step. Like we only have this sequence as a 4 time step sequence. There is no more dynamics as humans see, because we don't have access to the full representation of the fMRI. So we just simulate it in the very high level manner.
Right. So it's more of a qualitative comparison between a functional comparison between the representations that are learned and what they supposedly look like in these recordings, where stimuli that come afterwards are more active. That's the effect that we reproduce.
Yeah. Sarah?
Yeah, just to clarify, so the temporal resolution essentially is 4 bins, one for A, B, C, D. Yeah, okay. So it's
one
like the
for
average.
A, one for B, one for C, one for D.
Okay. But so what I'm just confused is does the, because you basically don't really have an actual temporal resolution apart from the average bin. Is it just about the boundary condition, basically going from one bin to the next? Or what would happen if you would try to really have a time resolved activity within, for instance, a stimulus A? Would that make a difference?
So not really. I mean, we can also try to add like, instead of having one hot encoder, like have some temporal encoding of each of these elements. I would say it won't change the results much. Something that is important to note is the basically prediction horizon that you choose to train the network. That has been shown to be quite important in how the network learns. For example, in the case of the speech data, a simple next step prediction does not work. You need basically to predict at some perceptual time step, for example, within 70 milliseconds. So you're not predicting the next time step, but what will happen 70 milliseconds later. So these perceptual time bins are quite critical in learning, at least in our models.
Okay, thanks.
Okay, so I'll move on to a little bit, probably a little bit more involved experiments, recordings from monkey prefrontal cortex on exposure to visual, local, global, deviant stimuli. This is a fully unsupervised exposure to such stimuli. After habituation, you just get exposed to blocks where there are local standards and local global deviants. So the monkey learns the structure, and it turns out that in the PFC, you can decode, there are directions for linearly decoding temporal position in the sequence of 4 elements, 1, 2, 3, 4, or there are directions for encoding what stimulus is actually currently visible, or like the presence of a local or global oddball. So all of these can be decoded. And so what we do again is expose RPL to sequences of this sort. Also visual, we in fact reproduce exactly the same images from this experiment, expose RPL to such sequences, and we do see representations that encode all of these quantities that encode for the sequence structure. In fact, if anything, it encodes it more robustly than people saw in the experimental data, but qualitatively, it matches. So that again, it's a very similar comparison that we observe the same representational coding in our model as people observed in experiment. So, right. So to conclude here, this section, we reproduce some experimental observations, again, at the functional representational level. And at this point, I think I will hand it over to Atana, unless there are any questions. Yes?
I have lots of questions, but I feel like I will if you have more slides, I'll let you finish. Maybe Tim?
Yeah, in the comparison with the actual experimental data, I think you mentioned that you were comparing the neurons in your model with fMRI, or was it EFIS?
Which one? So this was the macaque PFC. These were, I think, NeuroPixel EFIS recordings. The humans, that was fMRI.
Okay, I was going to say, because I remembered you saying fMRI. I'm like, I don't know, that's very different than looking at individual neurons, but the EFIS, yeah, I can definitely see. All right, thanks.
Right.
All right, so now something that might be more interesting for you is basically now we want to see how we can understand neural circuits through RPL in a more granular level. So far, what we showed, like, for example, in the PFC case, we had a very deep network that then we could match the representations of the integrator to the PFC of the monkey. And then the question is, if we have also recording of the sensory cortices, can we also show similar, basically representational similarity between the encoder and the sensory cortices, for example. So the deep RPL model that we have presented so far can address basically more in a network level. But if we want to look deeper into how like cortical circuit can be implemented, what we can do is, instead of using a deep encoder we can basically use encoders with like single layers or shallow encoders. Each of them have their own predictive circuits. So we have learning within each of these circuits, and there is no backpropagation of the error throughout the hierarchy. In principle, this can be mapped to cortical hierarchy in such a way that we have a bottom-up pathway through cortical layers, and then within each cortical column, we have these local predictive circuits. And here, really, the focus is to send the representations forward into the hierarchy rather than errors, which was the case in predictive coding principles. So we are sending actual information about what the sensory experience. And then this, which we call HRPL or hierarchical RPL, we basically train on the same animal data that we had in the beginning. And what we observe is that throughout the hierarchy, we can represent more and more of the latent variables. So if, like, for example, orientation might not be extractable from the lower areas, but as you go higher in the hierarchy, you can extract this information at a similar level to the RPL network that we saw before. Basically showing that you can train a hierarchical network in such and have the information of the latent variables, which is also quite missing in predictive coding computational models. What is still missing from this model is feedback connection. So the best way to do it is to basically let the integrators, which are making our representations, communicate with each other to fill in the missing information in the lower circuits. This is quite reminiscent of also dual counter-stream architecture, if people here are familiar with, where there are these two parallel bottom-up and top-down pathways in cortical hierarchy. And then there are interesting questions like how this feedback can modulate representation, both during learning and inference, and how this feedback actually affects the representation. Is it multiplicative, additive, subtractive, divisive? And we can basically look into these different feedback types as well. So within this architecture, we could not only look if we can find these four computational components that RPL suggests as basically circuit motifs, but also we can study how feedback can be modulating these network components. So this brings me to the outlooks of this project. The list is huge. I just summarized some of them. So the biggest building block for me is how feedback connectivity in this hierarchical model shapes representations. But a bigger question from theoretical perspective and computational background is why actually RPL and HRPL work? How do these structured latent representations emerge, and what are the inductive biases? And this is actually not only about RPL, but also generally in JEPAs. These are still quite a mystery and needs to be investigated further. Also, critical question relevant to biology is basically, can we explain some cortical motifs using RPL? As I mentioned, there are these computational components that we might be able to actually find cell types that resemble these computations, and then we can find neural circuits that can have similar representation to the model, basically. That would be a hope. And then another question is, how does this extend to multimodal settings? And the spontaneous one is sensory motor integration. A colleague of mine, Thomas, is actually working on this. starting from similar videos to the animals. Now he has moved to videos similar to what mice see in virtual reality during sensory motor mismatch experiments. And hopefully by showing same stimulus to both animal, mice, monkey, whatever, and the model, we can basically compare the representations within the model and within the brain for the hope to find basically a more structured mapping between the model and the cortical circuitry. And with that, we are toward the end. We are happy to answer your questions. We are also looking forward if you have relevant data that can be used to validate the model. And also we would like to also thank the whole lab for their valuable comments and feedbacks during this project.
Thank you for this wonderful presentation. I'm going to let people ask questions. I have also my own. Lucas.
Yeah, thanks. Fascinating talk. I was thinking or asking myself, how do you train the recurrent network? Is it with backpropagation through time, or how does it work?
Yes. Yes. For now, it is backpropagation through time, and in the hierarchical model, we are just easing out the constraint by not propagating the error throughout the hierarchy. So there is still backpropagation through time within each of these circuits.
So,
okay, thanks.
But there, I think several of the local, temporarily local approximations of BPTT presumably can help at least for short sequence lengths.
Yeah.
So that's definitely an open direction.
Okay, yeah. Like eligibility propagation or something, or
Yep.
Yeah. Okay. Thanks.
Okay, I have I think this slide is good. So here well, first we have tons of data. So we'll be really happy to collaborate in any shape and form for you guys to sort of see if our data can be informative of your models. These slides is making a proposal that different parts of the cortical layers might be implementing different part of your models. And we actually have recordings of all of those layers. At this point, we have many recording sessions. And so and you sort of started, I wonder if you have poked into your models that indicate certain things to expect. So for instance, here you have recurrence, there's a purely feed-forward components, there's a prediction error components, there's like 3 different types of blocks. And we record from those layers. So what would you expect from the neuronal recording if your model is correct?
So first of all, something that is really missing is in this current state of the model, we only have single model. For example, we only have a visual input. There is no action. And in most recordings, there is usually action integrated. So in that sense, some of the recordings might not be relevant for the hierarchical setting in this particular setup that we have now. But for Thomas, who has the sensory motor integration, that would also work perfectly. And what we expect to see is basically what we think we will see is if we have the same stimuli, we can basically do representation similarity analysis or other types of ablations on basically, for example, ablating the neurons in the recurrent integrator and see if the learning is corrupted or how the representations change in response to that particular intervention. If we have similar experiments done also in the mice after we have done this similarity representation, that we have the matching between these computation components and the cell types, we can actually then address these types of interventions and ablations in the model as well to have a better understanding of the causality and what affects what.
Right. There are also some softer predictions that we could extract. For example, these models, typically the learning rate for the prediction, the predictive part of the network, for example, the integrator and the predictor, is typically higher. And also just functionally, that's where the learning signal comes from. So you would expect the recurrent parts to learn faster to any given change in temporal statistics. So the representations will change first in the predictor parts and then in the feed-forward encoder part. So there are these, I mean, the headline experimental prediction here is that there is some purely feed-forward pathway to begin with, right? Like that's already like a
Which is
big
not
one.
only the error.
Yeah, it's not only the error. Which in experimentally should show up as, you know, if there is a part of the cortical column which doesn't actually recurrently affect and the feed-forward part of the cortical column very strongly, right? But it does affect learning, but not ongoing activity.
Yeah.
So that would be kind of important as well.
I wonder if one thing that's possible to do is because you're showing the type of latent that these models are extracting. Okay. In the literature currently, there's a little bit of a debate to what extent V1 is encoding time versus visual information. So for instance, for Zane and Ajafi group has shown very little encoding of time. Carlson Stringer group recently is sort of pushing the idea that it's possible that some of the but V1 is more encoding spatial information as well, like so that the sensory motor coupling is mostly implementing by spatial information, like the screen is coming in, and so that so the experiments are pointing to certain types of latent that are extracting by V1. And so I wonder if there is something that could be done here where you sort of play with the information that comes in and then see what types of latent are extracted by your models to see what are the ones that are implemented in the real V1. Because I think that the tension is we don't really understand what V1 is learning. I mean, there are all of this work that I've shown receptor field and so on and so forth, but it's clearly learning more than just receptor field. And so I'm curious if it's something you're be interested in exploring.
Yeah, so something that is really coming out of the model is that we can read out information to some degree at each cortical circuit in the hierarchical motor, for example. So that is something that we find quite critical to also like see in neural data, because there are also these like evidences that are not concrete really, but some people show that you have selectivity to different features in different areas, whereas some people are showing more area-specific responses and feature specificity in each area. For example, we have the what and where pathway, and you cannot have information about the other in the other pathway. So these are the type of questions that we are also quite interested in, if there are basically data that we can address such tensions, because something that comes from our model is that you can learn this to some degree at each basically area. And then the question is, what is the expectation from each area?
Right.
And presumably you can add additional inductive biases to the learning of each of these areas or circuits to match it more toward what those areas can learn in the brain.
Another thing we didn't actually present because we didn't look into it too deeply, but there are these hypotheses from Eero Simoncelli about perceptual straightening across the visual hierarchy, where straightening in progressively representational trajectories, they progressively get straighter across the hierarchy, across the visual hierarchy, meaning across time, these trajectories become more and more linear through time. So that's something we do observe in this model, but we don't have a very principled comparison, but that's another way to compare. Just by looking at what the representational trajectories through time upon exposure to sequences or naturalistic video, what these trajectories look like in the model versus in the model components versus different parts of the particle column.
Makes sense. The experiment that we have run over the winter that was designed as part of the review, I think is very good for comparing different types of prediction context. And so that's the first thing. So you have 4 different types of learning that could occur passively. And the second is we are recording across multiple points with multiple modalities. So we have lots of recording in V1 and LM, so the next stage. We also have recording in the prefrontal cortex and the motor cortex through the neuropixel. So I think what you could do is train your models on the different prediction context and extract the latent that you expect to see and compare what's latent across the activity with the activity we see at different levels of the hierarchy, because we are going to have prefrontal cortex where you might expect more recurrence, so longer integrations. As you said, it's likely that uh, the predictions is the window, the area might be predicting further into the future depending on where you are, right? And so I think that would guide the kind of latent that I extracted at each level. And so I think this is something that could be done to compare with our data. I mean, I'm sure there are other experiments in the field that could also do that.
Yeah, that's nice.
And our data is publicly available already. So if you wanted, you could start already today.
That's good. But just to make sure, what is the stimulus?
Right. So we have different visual stimuli. So some have a particular temporal structure, right? And so the temporal structure increases. So some have a very local oddball kind of a structure. Some have a global oddball kind of structure. There also are contexts where there's a motor input that is involved in the learning. And then there's also type when we change the durations of the drifting grading. So I think this is likely going to recruit different set of areas or layers depending on the context. So I would be curious to see what does your model extract in the different context.
Yeah, that's.
I don't know how much work it is, but.
Yeah, we can try. It will probably take a bit of time to set it off, but yeah, that's doable.
I can share with you the data release paper and review that sort of explain those experiments if you're interested.
Yeah, sure. Thanks.
I see Sarah has a comment. I don't know if you're here.
Yeah. Is it possible to dissociate contribution of stimulus offsets from stimulus evoked activity?
What?
Not sure I fully understand this.
Yeah, I also don't get it.
I'm not sure I understand either. Sarah, are you here to clarify her? Maybe she's in the commute. Yes, she's in the commute. So I'm assuming people can reach out to you if they're interested in collaborating.
Yeah, sure.
We are at the hour. Do you have questions for us?
No, I think that's fine.
Okay. Well, thanks so much for presenting. I think it was a very interesting mixture of models and neuronal correlate, and we'll keep in touch.
Cool. Thanks for giving us the opportunity.
Thanks. Thank you.
Thank you.
Thanks.